Hello, hello, wonderful chemistry 20s. We are moving on to one of probably my favorite equations in Chem 20. This is kind of a fun one to manipulate. There's lots of neat stuff going on. This is the ideal gas law. And the reason why it gets this fancy word ideal, we go into more if we'd been in your regular class, but ultimately it's a situation where the equation applies as long as we have ideal gas conditions. Now, this is a circumstance where does ideal really actually exist all the time? And not so much. But we end up with numbers that are accurate enough that they're still really, really useful, even in a normal world situation. Now, each thing that's there all revolves around this new variable, a new constant, if you will, called R. Good news about R is you don't have to memorize it. It's on your formula sheet, so if you're looking for it again, that's where it is, no problem. But what this stands for is the universal, whoops, there we go, that's supposed to be an N. Let's do this again, come on. All right, universal gas constant. And the key thing about the universal gas constant that I think is so helpful is the units, because the units give you a hint to all the rest of the variables that are part of that ideal gas law. So check this out. I know these are written in kind of a weird way, but ultimately what this means is liters times kilopascals, and that whole thing divided by moles times Kelvin. Now, think about each of those individually. If you consider, for example, the kilopascals, this is a major hint saying that, hey, P is equal to pressure, and that's familiar from when we did the combined gas law, but no exception, all the time, you need to make sure your units for pressure are in kilopascals. Again, look at another one. Here's L, okay? L stands for, well, something familiar to us again. L is your volume, and we've been working with that already as well. Now, anytime now that you see something in milliliters, kiloliters, whichever, you have to know absolutely 100% every time convert it to liters. Okay, check out moles. Moles is familiar, especially from the lesson we did yesterday or whenever you decided to work through it, that talks specifically about molar mass and the mass amount calculations. N is a part of this one. So N is number of moles. So it was worth doing those equations in the last lesson. And of course, that's in mole. Temperature, I have said this before, I will say it again. Temperature absolutely has to be in, no exception, Kelvin. And that's why the practice that you put in before is a good one. So temperature, and once again, you're going to have to convert anything in degrees Celsius into Kelvin scale. All right, PV equals nRT. A formula you don't have to memorize. It's on your formula sheet, but one you'll use so much that by the end it'll probably be stuck in your brain. Now, again, I cannot emphasize enough about that universal gas constant. Really, like I said, pay attention to the units. It's a lovely little cheat to help you know what units you need to use for each of those variables. And it is on your formula sheet. You always have it, which is a really, really nice situation. Starting to go through examples. Let's check these out. Similar thing as to what we did before, where you just have to think in terms of what have you been given? What are you looking for? Do you have correct units? I want to emphasize this again. A lot of students get mixed up on this word amount. Don't let that throw you. When you see amount, you have to know that a question is looking for moles. Okay, so that was sort of new from yesterday. Perhaps in grade 10 you use that sort of language, but amount is moles and moles. Next thing we have is a pressure of 300 kilopascals. That's pretty easy. That's definitely going to be pressure. And 20-liter tank. Remember what I said about paying attention to the units. If you see liters, you've been given a volume, for example. And last thing we have here is 40 degrees Celsius. Take note again of those units. Degrees Celsius isn't good enough. We're going to have to convert this to Kelvin. Don't make these harder than they need to be. Similar type thing to what we did before. Write down what you know. We're looking for N, the number of moles. Pressure is right there in front of you, given to you. 300 kilopascals. Once again, writing things at just numbers is not good enough. You must include your units. Volume, 20.0 liters. Yes, include the zeros, they're significant. And temperature is 40 degrees Celsius. I'm at the point now, guys, where I wouldn't expect to see the work for changing temperature. I usually just draw an arrow at 273.15 on my calculator, and we get 315.15 Kelvin. Alrighty, next step is write down your whole equation. PV equals nRT. We have an equation with 5 variables, so you bet you need to use algebra in order to properly isolate the amount. Okay, think about what's happening here. You can get rid of the R and the T at the same time. They're both multiplying n. The opposite of multiply is divide. And like I said, you can get rid of both at the same time. What you do to one side of the equation, you do the other. These are now canceled out. If we summarize that, N is going to be equal to the pressure times the volume over universal gas constant times T. Don't forget about that R. It's not in the question, but technically every single time you know you've got R. 8.314 liters per kilopascal over moles times Kelvin. Now, R is a pain. It's hard to write it out every time. It's annoying to have all those units. You need to. If you just write 8.314, the number doesn't mean anything. So deal with it, get into a habit, write the units, please. Speaking of which, start plugging things in. 300 kilopascals for the pressure times that volume of 20.0 liters. That whole thing is all over 8.314 liters times kilopascals over moles times Kelvin, multiplied by the temperature in Kelvin, 313.15 Kelvin. The units have to work. Kilopascals cancels out kilopascals. Liters cancels out liters. Kelvin cancels out Kelvin. We're left with moles, which is exactly what we want. That's the goal of the question, is to look for N. You end up with an N equal to 2.3045 ... moles. Look back at the original. We're allowed 3 sig digs. That 300, 20.0, 40.0, 3 sig digs. N is equal to 2.30 moles. You must include that 0. If you leave off the 0, you're not making 3 significant digits. All right, hopefully that felt decent. Let's try another one where we're solving for a different variable. Okay, check out this one. Again, focus on what the question is asking. Calculate the volume, V, occupied by 0.883 moles. That's N. This is a big hint. The instant that a question mentions moles, mass, an amount of any kind, then you know that you're going to have to use the ideal gas law. PV equals nRT. Because the combined gas law never involved an amount. So watch for stuff like that. There's other hints built in. Often knowing what the actual gas is really helpful. It doesn't really factor into this one, but wait for it. You're given pressure and you're given temperature. Notice that your temperature is in Kelvin, so we're going to have to change it. Okay. Purpose of the question, looking for volume. Volume equals question mark. N equals 0.883 moles. Yes, I want you to write your givens each time. Get into the habit, continue the habit from our other questions. Pressure is 120 kilopascals and temperature is 120 degrees Celsius. But once you add that to 273.15, you get 393.15 Kelvin. And of course, you always have R. Okay? Our goal of this question is to look for volume. So we're trying to get V by itself. Don't make this harder than it needs to be. To get V by itself, we do the opposite, which is divide out by P. We do to one side, you do the other. Those are gone. As we keep going then, V is going to be equal to N, which is 0.883 moles, times R. Write out the whole thing. 8.314 liters times kilopascals over mole times Kelvin, times our T, 393.15 Kelvin. Remember, that whole thing gets divided by our pressure, 120 kilopascals. I keep emphasizing this, and I will keep on doing it. Cross out the units. Make sure things make sense. Moles are canceled out, kilopascals are gone, Kelvin's gone, left with liters, which makes sense because you're looking for L. At the end here, we can answer V equals 24.0518. It keeps on going liters. 3 sig digs is our goal, 24.1 liters. Done and done. And honestly, guys, these aren't so bad, right? This is just single variable, no big deal. But what if we start to introduce the same formula that you used yesterday? So if you have a situation where I'm not giving you anything in moles, or you're not looking for moles, but instead it relates to mass. Okay, don't get sidetracked. Remember, it all relates back to moles. And from yesterday, you know that we can use the formula N equals mass over molar mass to relate mass to moles. In other words, we're going to be using two formulas at the same time in order to get to the answers that we need. Okay, let's keep going. For example, different question here. It doesn't say what amount, it says what mass. So think about this. Suddenly, this is M, which isn't in PV equals nRT. So that means we're going to have to do something extra. Huge hint that hydrogen gas is here. Hydrogen gas is part of Hofbrinkel. Don't lose sight of that. H2. The rest becomes very familiar. 45 liters. A volume. 75 kilopascals. Right. Pressure. 290 Kelvin. Yeah. There's your temperature. Okay. When you build what you know, ultimately, if we're looking for mass, and you think about PV equals nRT, out of those 5 variables, the one that actually relates to mass is N. So that's what we need to look for first, because then we can use that N in order to help us get to mass. Okay, let's begin. Same as usual, write down what you know. Volume, 45 liters. Pressure, 75 kilopascals, and temperature 290 Kelvin. R, of course, you have. We're going to start by looking for N. PV equals nRT. Your goal is to get N by itself. We're going to divide by the RT on both sides. N is equal to PV over RT. Pressure, 75 kilopascals. Volume, 45 liters. Divided by R, 8.314 liters times kilopascals over moles times Kelvin times that temperature, 290 Kelvin. Now remember not to round. We're going to have to use this number again, guys. We get N equal to 1.39979, keeps on going moles. And this answer is really important because we're going to have to use it again. Okay, so here's your N. Now, if we continue on, we can take that and be like, okay, how do I relate N to mass? Oh yeah, by this. N is equal to mass over molar mass. That goes back to another given then. We're going to need the molar mass of H2 gas. So our givens have an extra from what we've been doing so far. 1.01 times 2 is 2.02 grams per mole. Now we're looking for mass, which means we're going to have to rearrange this in order to get M by itself. No big deal. Times by molar mass on both sides. And we've got it. This is going to cancel out. Mass is equal to the number of moles times the molar mass. We have the number of moles. You figured it out before. 1.39 moles. It keeps on going. Times the molar mass you just figured out for hydrogen. 2.02 grams per mole. Remember where numbers have come from. This one came from here. It's already in your calculator. Keep it there. Just multiply it by 2.02. And our end answer, once you do that, we get 2.8275 ... grams. The question has 2 sig digs, that 45 liters, the 75 kilopascals. So the mass of the gas is 2.8 grams. I find, guys, when I'm writing out my givens, it's really, really helpful to actually write out the molar mass of the gas right from the beginning. That way it's already calculated, it's in front of you, and you're not having to redo it later. Assume that this is now one of the givens that you're going to need. All right, almost done. Let's do one more question, and then you can start working through problems. Once again, when you read through a question, look for a hint that this is ideal gas law. And there it is. There is some mass which relates to amount given to you in the question. The purpose of this one is to look for pressure. Now, if we're looking for pressure, we're given temperature, we're given volume, and we have an amount. Definitely ideal gas law. And like I said before, never lose sight of what type of gas. Oxygen gas, part of Hofbrinkel, so that means that it's O2 gas, which makes a big difference for molar mass. Here's what I mean for writing down everything. So I'll always put down what I'm looking for, P equals question mark. And then I'll keep going. I've been given a mass, and that's super helpful. Mass is equal to 50.0 grams. But right away then, I'll go to molar mass and have that down too. So molar mass of oxygen gas, 16.00 times 2, 32.00 grams per mole. Keep going with what you know. Temperature is 40 degrees Celsius. Add that to 273.15. We get 313.15 Kelvin. And my volume, of course, is up there too, 100.0 liters. We have R. That's supposed to be a question or a check mark. There we go. All right. Step 1 is we can't do PV equals nRT to find the pressure until we have the number of moles. Now that's missing at this point. So start there. Focus on getting the number of moles first. And you've got everything you need in order to do this, right? So if you take that formula, we know that N is equal to mass over molar mass. And lo and behold, I've got mass and I've got molar mass. Check, check. We're good to go. So keep working through. Mass, 50.0 grams, divided by that molar mass, 32.00 grams per mole. Remember not to round. You're going to have to use this number again. 1.5625 moles. There's N. Take note of this guy. Don't lose track of it. We'll need to use it in our PV equals nRT formula. Speaking of which, let's go to that now. PV equals nRT. Goal of the question is to find pressure. All right, so let's get it by itself. Divide by V on both sides. We're good to go. Pressure is equal to N, the number you just found, 1.5625 moles, times R, 8.314 liters times kilopascals over moles times Kelvin, also multiplied by the temperature, 313.15 Kelvin. That whole thing is going to be divided by the volume, 100.0 liters. Our pressure, once you number crunch all of that, 40.6801 kilopascals. And with our required 3 sig digs, 40.7 kilopascals. There it is. There's a decent chunk of questions on ideal gas law that you need to work through. And they're all due for the assignment. This is an important law for you to get used to, for manipulating formulas, for understanding how units are canceling out, for making sure that you have a good awareness of how gas laws work and how we're able to use them with amounts. So here's your focus of questions, guys. There's quite a few of them, 6 of them today for you to work through. Have a great rest of your day, and I will talk to you again on the next podcast.